One of the really cool things about covalently bonded substances is their infinite variety. And a nice shortcut to use to come up with chemical structures is to recognize that oftentimes for these covalently bonded substances, and that means nonmetals, and that typically means hydrogen, oxygen, nitrogen, and carbon. Those are the four most common ones. A nice shortcut is to recognize that they form 1, 2, 3, and 4 bonds respectively. In other words, honk if you love chemistry, HONC, 1, 2, 3, 4. So you can quickly start assembling substances, first drawing your backbone. That would mean, in this case, your carbons, since they form the largest number of bonds, and then attaching around or perhaps inserting in between those other atoms. Oxygen can go in between. Hydrogen cannot, since it only forms one bond. It's always on the edge, if you will. And come up with a formula. We can draw this either structurally or skeletally, and that's what we're going to show you in this screencast. C3H8. Well, draw your three carbons first if you're going to come up with a formula, meaning a bond structure, a real look at that molecule. And then throw your hydrogens around, and you'll see that it fits just right. No double bonds, no triple bonds, no rings, no funny business. It's just C3H8, and the skeletal formula can be drawn as well. By the way, notice that when you only have three carbons like this, there's only one way to draw that. These things can bend. These things are like propellers. They can rotate. So if you move these hydrogens around a little bit, it would not be an isomer. It would not be a different form of it. And if you did not bend it, but drew it all linear, for example, that's not an isomer. Isomers are really different arrangements of the atoms, and there's no possibility of rings or branching in this particular case. You only have a line, three things. You'd need a fourth one in order to get a branch. So that's it. That's the only way we can draw C3H8, and by the way, this is propane. To draw it skeletally, this is something the experienced scientists really like because it becomes a hassle to draw all these hydrogens and all these carbons and all these bonds. Imagine, C10H22, for example. Ugh. So they just omit the carbons and the hydrogens. They just show the carbons as bends, if you will. Any end or bend is a carbon. So there's a carbon in the center, and there's also a carbon at the end and the end here. Hydrogens are implied based on the honk rule. Therefore, we have three bonds remaining, right? Carbon forms four bonds, so we have a CH3 there. There it is over here. CH2, can you see that? Two bonds, therefore two hydrogens. And CH3 just like on the other side. Notice also the symmetry of this thing. If we flipped it over, we'd have the same molecule. And so this is propane. Let's try to draw C2H6O. Well, there are actually two ways you could draw it. You could put the oxygen in the center. Oxygen acts as a spacer, if you will, since it forms two bonds. It squeezes in between things. But you could also put it on the end, couldn't we? Right? So these are two substances, both C2H6O. Take a second and make sure that the honk rules are obeyed, and they are. These are called isomers. If you're curious, this is called dimethyl ether. That's an ether functionality. This is ethanol or ethyl alcohol, where that's the alcohol functionality. And if you want to draw it skeletally, wow, it's super brief. There it is for dimethyl ether. That's an end and that's an N, so that's CH3O, CH3. Don't be led to believe that there might be a carbon there. Draw it nice and close so that you recognize that this is a chemical bond between carbon and oxygen. After all, this is just one substance here. And here it is drawn for ethanol. Now, technically, that H could be dropped, as implied. There would be one there, but they usually put it in there to show you the alcohol functionality, since that's an important part of the molecule. We could draw C3H6O2. I do this for two reasons: to show you that creativity can come into play, since these things can form ring structures. Notice that we have a lower ratio of hydrogen to carbon here. It's 2 to 1, where it's 2n plus 2 there. 2n plus 2 always implies no double bonds and no rings. When you have less than that, you can have a double bond or a ring. Boy, we could put those oxygens lots of other places. And in fact, here's one of so many ways to draw this formula. This is one possible isomer. And I wanted to show you a little bit about what's known as stereochemistry. That's a wedge, that's a hatch. That means that alcohol functionality is coming out of the plane of the board towards you. That alcohol functionality is being pushed away into the screen. And so it would be locked in place, since if you have that ring, it no longer can rotate. So that would be structurally, and here it is skeletally. The H's are shown to show the dialcohol or diol functionality of that substance. This is a little bit about structural and skeletal formulas.